bit about, okay. And she's going to discuss or talk to us about the mystique of quaternion spin from Rodrigues, Hamilton to Pauli, Dirac, and Hestenes. So thank you very much for speaking to us, and now take it away.
Yeah, well, thank you for changing the title. You made it quaternion spin, which is what exactly it is.
My quantum spin. My brain's so quaternion.
Yeah, well, that is precisely. So, thank you so much. I want to thank the organizer for telling a story of a physicist. I'm a physicist, actually, giving me opportunity as a physicist to talk to mathematicians and tell them about this mystique and the story of quantum spin, which is really a story of quaternion in the minds of physicists. Okay, so it's sort of, so I guess Johannes said it just right. He made it just perfect, actually. Maybe that's what I should have had in my title. Okay, so, let me start out. Sorry? Yeah, sure, go ahead. We are all made out of atoms, but atoms are made out of elementary particles, and those are electrons and quarks. Quarks are basically protons and neutrons. So the funny thing is these are elementary particles. That means you cannot break them up. They are point particles. And they are kind of mysterious in the sense, let me get to my, so as I said, these are elementary, and however, they have mass. Okay, so they are point particles, they have mass, they have charge, which is not too mysterious. But the funny mysterious thing about them is they also have something called spin. Now, can you imagine a point particle which is spinning? Well, that's beyond our intuition, right? You cannot imagine a particle which is a point particle but it's spinning. So these are some kind of mysterious angular momentum, mysterious ballerina, and it's spinning all the time. And this spin of all these particles, electrons, and is actually intrinsic and exactly has the angular momentum equals to h bar over 2, where h bar, if you ever heard of quantum physics, you probably know what h bar is. If not, just think of some fundamental constants, like in classical physics, you have speed of light or gravitational constant. In quantum physics, there's this one beautiful constant h bar, okay, coming from Planck. It's called the Planck's constant divided by 2 pi. So anyway, all these fundamental particles have this strange, mysterious property called spin, has angular momentum exactly equal to h bar over 2. And that's not the end of the mystery. There's something else going on with this spin, because in quantum physics, you describe these particles by wave functions. And it turns out that if you rotate under rotation, these wave functions actually change sign if you make a 2 pi rotation. Now that's kind of weird, right? When you rotate something by 2 pi, you're supposed to get back to your starting position. But these wave functions, which describe this quantum spin, actually they don't come back home. They actually change their sign. So they are neither scalars, they are not vectors, right? Because scalars and vectors, that's not how they transform under rotations, and so they are called spinners. So this is this sort of remind you of the Mobius strip, right? The Mobius strip, you have to go 4 pi rotations before you come back. So spinners are sort of like vectors on a Mobius thing, on a Mobius strip. And as I say in the last sentence of my talk, why am I talking about spins in a quaternion session? Because to physicists' mind, quantum spin halves are quaternions in disguise, a reincarnation of, and that's my story that I'm going to talk about. So since a spin is going to start with rotations, of course rotations we know started with Euler, and 1975 Euler was already blind. Actually, and that's when he told us how you describe rotations. You describe by angle and an axis. So you have this one axis of rotation and angle that fully describes the rotation of a body. And what Euler showed was that if you take 2 rotations, so I'm representing rotations by r theta. I hope this this notation is clear. So he's either represented rotations with angle theta and the axis. Yeah, everybody can see that, good. And Euler also showed that if you have two different rotations, let's say one rotation by angle beta and axis denoted by m hat, another rotation by angle alpha, axis denoted by L hat, the product is another rotation, which is the R gamma n. So that's a big contribution. Everybody's heard of Euler, and we know that he actually did that in 1975. Now, Euler didn't tell us, actually, if I give you alpha, beta, what is the gamma and n? Okay, he didn't give you the rule. If you're given two rotations, how do you determine the final rotation in terms of the two original rotations? And that was done by Rodrigues in 1840. Now, let me just, out of curiosity, ask how many people have heard of Rodrigues? Not many, but if I say how many people have heard of Rodrigues in rotations, the number is even small. And it's kind of sad because he's done some iconic, remarkable work, and it's sort of invisible in the field of rotations. Unlike Euler and Hamilton, like the, who are our heroes, somehow he's remained in the background. Anyway, so what Rodrigues did was given by this what's called the product formula. So it tells you if you have two angles, alpha, beta rotation, the final angle of rotation is given by this rule here. And the second equation tells you the axis of rotation. This is such a beautiful formula. You cannot derive it in a very simple way, but actually Rodrigues derived it in a very sophisticated mathematical craftsmanship, I should say, and that was all written in French, and lately Peter Friedberg, with the help of Johannes, actually have translated Rodrigues' 1840 paper, 60 pages long paper, a French paper, into English, and now we even have the proof of the original formula of Rodrigues that's given by here. Okay, so anyway, the most important part of this whole thing is, what you notice is that you're describing rotations by angle alpha and beta and gamma. However, what's appearing in the formula is alpha over 2, beta over 2, gamma over 2, right? Half angles. And that's kind of very interesting. And certainly very interesting part of the spin story that I'm going to say. It's sort of like, somehow to me, that was like the beginning of spin, as you will see, in some abstract form in Rodrigues' formulas. So I'm going to come back to this importance, significance of these half angles, but I just want you to remember that this is the first time, actually, in the history of history of rotations, that rotations by angles given in terms of half angles. Very peculiar feature. I mean, I find it peculiar, actually. I don't know how you feel. Okay, so let's go on and we'll see how it sort of really relates to the spin. So of course you all know about quaternions. I'm not going to actually talk much about it. 1843, Hamilton discovers quaternion, and it's a non-commutative. He describes. So I'm going to skip all the story about Hamilton because I guess you're all experts on quaternion. So you represent your quaternion by this formula here, and this ijk obey this non-commutative algebra. The important point, again, the important lesson for this audience that I want to point out is that the quaternion algebra is identical to what's called the Pauli spin algebra, the spin algebra that I'm going to be talking about later on. They are identical. So these Pauli spin matrices, now quaternions for 1843, right? Pauli matrix is going to come back in 1925, right? Almost a little bit less than 100 years old, but they have exactly the same algebra. So, don't worry about it too much, but I just want to say that, in fact, right now all you want to think about is this ijk you could represent them as matrices 2 by 2, and if you multiply them by I, they have exactly the quaternion rules. Okay, so don't think about spin at this point. All right, the second thing I want to point out is right here. How does quaternion describe rotations? This is the formula, right? Again, you notice the half angles. Hamilton was very puzzled by it. He didn't know what was going on, and this thing came much later. But anyway, the half angles did appear in the mind of mathematicians studying rotations, a lot before anything happened in physics or in spin. Okay. Let's move on. Before I get to really the spin story, I have to give you this mathematical background, and just want to mention quickly, get back to this geometric algebra. Right now, so far we've been talking about algebra. Now let's talk about geometric algebra, which is a Herman Grassmann and Clifford algebra. And again, this is another story by itself, but just to mention is the most important thing I want to point out is that the problem is how you multiply vectors, right? Even now, it's kind of a weird thing. Vector multiplication has been always a weird thing in mathematics. So anyway, I guess Grassmann is considered the father of this geometric algebra, and he defined this vector product. It's called the geometric product in terms of something called the wedge product, which is more like a cross product. Now the whole formula of the geometric product is given by this. It's got two terms, scalar product and something called a y-vector. So it's a scalar. I'm just showing you why this quantity is a scalar. You can sort of easily see. And so this scalar is the symmetric part, and the wedge product is now called the outer product. It's actually an anti-symmetric part of this thing. Again, why am I bringing all this? Because it turns out that geometric algebra, the Clifford algebra in particular, is actually the algebra of quantum spin. So the quantum spin appeared so much later in physics, it was discovered, but it existed in the minds of mathematicians so much before all there. So the mathematics was all there, so it existed some kind of abstract thing, right? When we did write Clifford algebra, now we think, those guys knew quantum spin. Of course not. But they knew something which physicists later on use as quantum spin, which will be the story later on. Okay. Just to give you an example of Clifford algebra quickly, I like to sort of give this thing, just let's go to 3 dimensions. Take orthogonal vectors. Orthonormal vectors, E squares is 1, vectors are orthogonal, and if you work through the algebra, you see this very interesting relations like 2 vectors, E2, E3 is I times IG. Sorry, I should define what is IG. IG is actually what's called the highest grade multivector, E1, E2, E3 in 3 dimension. And it actually turns out to be pseudoscalar, and that this is the algebra here. If you just look at this part, sorry, I guess this thing here, that's the algebra in 3 dimensions, the Clifford algebra. And again, surprisingly, that's identical to Pauli spin algebra that physicists use to describe quantum spin. But it existed a lot more before that. Here, just if you're not familiar with this wedge product, here's a slide sort of showing you that this outer product or the wedge product is really the area for this parallel line. Okay. So when Clifford was, Clifford and Grassmann were sort of working at the same time, and when Clifford was he was familiar with Grassmann algebra as well as the quaternion, and he was wondering where are the quaternions in this, and actually quaternions turns out to be nothing but bivectors. So this is the whole interesting part of the story. Johannes can tell you a lot more about this. But the main point I want to mention is that this ijk, those quaternion non-commuting algebra that satisfy are nothing but bivectors, okay? They are not vectors. They are actually bivectors in this product. So you can define a unit bivector like this, and this is the one we saw was actually causing rotations in the previous slide. So bivectors, again getting back ahead of the story, bivectors are going to be the spinors, describe spins, and they are explicitly linked to rotations because bivectors are quaternions. So I'm trying to kind of set up the stage for introducing spin in some sense. So let's summarize this. I guess 2 years ago, David Hestenes was here and he talked about all this geometric algebra, which is a fascinating field. And basically, when you define this geometric product, you mix scalars and vectors, and sort of this is sort of what I'm summarizing. The most interesting part is that this algebra is associative, like that I've shown at the bottom. Cross product is not associative, but the geometric product is associative. And for us, the most important part, I think, is the fact that the bivectors are going to be describing the spin. So bivectors themselves form a subalgebra of the full algebra and this spin. Okay, I worked out some example. If you want to, as a physicist, if I don't understand, if all this sounds too abstract to me, I just take an example. Take a vector A, take a vector B, compute a cross product, compute outer product, inner product, and check it out loud, rather than trying to prove it mathematically, why this is the case. So a very simple example here actually proves that this outer product or the wedge product is related to cross product by this simple formula. Okay, so I'm almost ready to go to quantum, to physics. But I want to point out this is one of the most important slides in my mind, because as I'm going to tell you in a minute, the spin in physics was discovered in 1925. However, in 1913, Cartan, this French mathematician, actually constructed spinors. He really did that, and it's such a beautiful construction. I hope you'll agree with me. Basically, what does it mean by constructed spinors? Now remember, spinors are the quantities which change sign after 2 pi rotation, right? He exactly constructed this, and how did he do it? Well, he took a vector of 0 length. Now what do you mean by a vector of 0 length? The way to imagine is take 2 vectors, let's say P and Q are orthogonal, and put them in a complex plane like this. And you can see the resultant vector is going to have a 0 length. And then he introduces 2 symbols. So you have vector component x, y, x1, x2, x3. He computes, he defines two numbers, psi1 and psi2 by this formula. And I'm just skipping all these details. The most important point is x1, x2, x3, they transform as a vector, but the psi1, psi2 have these half angles. So Cartan in 1913, I guess 12 years before spin was discovered in physics, actually constructed the spinors mathematically, exactly, and a very simple construction. So he already kind of conceptualized that something like this should exist. At least this should exist in an abstract way. So this is a very, very beautiful construction. And in fact, I think I say that in this slide here, say one of the principal purpose of the work is to develop systematically the theory of spinors. And then he says, thanks to the geometric origin, the matrices used by physicists in quantum mechanics turns up by themselves. So in fact, I forgot to point out, if you go back to my construction here, these Pauli matrices appeared in his construction. Now Pauli matrices came 12 years later, Cartan, but so this all existed in mathematics before actually they appeared in physics. Okay, this is one of my favorite, that was one of my favorite slides in a work of mathematicians in terms of spins. Now let's forget mathematics and go to the world of physicists. And I want to now bring you the story of spin as it happened in physics. So now we're going back to the beginning of the 19th century again. And physicists were studying spectrum, hydrogen spectrum. You know what I mean? Lines, look at the hydrogen radiations coming from sun, and they have these colored lines. That's called the spectrum. And one of the interesting questions they wanted to answer was, what happens to the spectrum when you apply magnetic field? Okay? Because it turns out that Maxwell at that time has said that nothing is going to happen. If you put the spectrum, the lines in a magnetic field, they're not going to change it. Frequency, they're not going to change anything. So however, Dutch physicist Zeeman was the first one who studied this, and in fact, the reason I guess at Maxwell's time they didn't discover this because they didn't have strong enough field, they didn't have good instruments, but he was able to show that a single line, suppose you have one line like a red line from the spectrum, if you apply magnetic field, it splits into 3 lines. Okay? And that's called Zeeman effect in physics. Just take it like this. And the interesting thing is, it's very easy to understand even classically. Now this happened in 1896. This is before the electrons were discovered. Nobody even knew what the electrons existed. And all they were thinking about was, you have some charged particle oscillating in a magnetic field, and if you compute the frequencies, you have 3 frequencies. In the presence of magnetic field, you get 3 frequencies, and that's what the 3 lines are. That's called the Zeeman effect, before the electrons were discovered. And that's fine. However, it turns out just within a year later, Thomas Preston, Irish physicist, actually discovered that sometimes the line splits into 2 or 4, not 3. And nobody understood this. Nobody had any clue how can a single line split into not 3. The only thing they could think of was 3 lines. Anyway, just move on to the story. Electrons was discovered. Some of you may have heard of what's called the Bohr model in your, things where you understand how the spectral lines are, how radiations are emitted. Electron is described by some quantum numbers, and you go from one orbit to the other, you emit these lines, and it turns out this quantum theory also explains Zeeman effect. So Zeeman effect is very strange. What's called the ordinary Zeeman effect. One line splitting into 3 can be explained both by classical theory as well as the quantum theory. Not many phenomena are like that, but it's just one strange example. Anyway, this was all good. However, remember the anomalous effect that I talked earlier, right? The doublet. This is called a doublet or quadruplet. That is what's called the anomalous effect. People could not explain. A lot more anomalous effects appear later. I'm not going to go into the detail. And so to understand this anomalous effect, like one line splitting into 2 or 4 and not 3, is called the anomalous Zeeman effect. And to explain that, 2 physicists, Goldschmidt and Uhlenbach, actually proposed that electron must be spinning. Okay? Because it has another additional motion. And it turns out, again, we don't have time to talk about it. Once you have electron having some additional degree of freedom, they were able to explain this doublet that I was talking about. This is again a beautiful history in physics. It turns out, I should mention certainly one thing, Goldschmidt was actually a graduate student when he made this proposal. And when he wrote his paper, he gave it to his professor, and next day he realized something is wrong with his paper. And the professor says, well, it's a good idea. It may be wrong, but you don't have a reputation, so you have nothing to lose. So let's go ahead and publish it. And I don't know, for some reason, of course there's a reason why Goldschmidt and Uhlenbach thought the paper was wrong. They proposed spin, they wrote it up, they thought it was wrong. because classically it actually seems to be something going wrong with this. Anyway, so next day they go to professor. He says, well, I've already submitted your paper. Don't worry, you don't have any reputation, so what? So it turns out actually the idea was, everything was correct. And this is how the spin was born. This is sort of the birth of spin was postulated, explained the doublets and many things. This is sort of all ad hoc theory. Let me just go back to understanding quantum spin a little bit more, how you mathematically describe it, because in physics things are done in 2 or 3 parts, right? First part is, well, it doesn't matter, the order is not always the same, but one way is you experimentally discover something, right? And then you sort of do some kind of ad hoc theory, somehow try to, somehow do some kind of trial and error theory. And third part is to come out, get that effect really from a fundamental things. And all the 3 things happen in quantum physics, in spin theory. So first we already described Uhlenbeck and Goldschmidt and Uhlenbeck. They proposed the theory just kind of as a postulate, explained everything. They just worked out the formulas. Then, of course, came the Schrodinger equation. This is the main equation in quantum physics. Non-relativistic particles are described, not by Newton's equation, by Schrodinger equation. And you have this wave function. And to incorporate spin, how do you incorporate spin in Schrodinger theory? Well, I don't think there's any point in my lecturing on quantum physics, but simply just to mention that if you don't know any quantum physics, just remember all you have to do is change the energy by those two, that operator, the momentum by that operator at the top, and you sort of get the Schrodinger equation. Anyway, so the basic idea is you describe the thing by a wave function, and the Pauli was the one who said if you have a spin, then you need wave function should be 2-component wave function. You should go spin up and spin down. And once you do all this math a little bit, here are born the Pauli matrices that we have been talking about, which existed in the minds of mathematicians, even starting with quaternions and starting with, with Cartan and all that. So they were proposed in 1925 by Pauli. Pauli had never heard of Cartan. I mean, or at least had never heard of his work that actually he had used his matrices. So this was totally an independent discovery. And so Pauli matrices sort of describe quantum spin, okay? So they obey non-commutative algebra, and this is sort of our thing. So just to reach, as I said, the third step, of course, came. Again, this was an ad hoc theory. Like Pauli didn't have a reason to say. He just said, if I assume the wave functions have 2 components, I can explain everything, right? And he got the Pauli matrices, he got everything, but that's not really understanding where the spin came from. And that work was done by English physicist Paul Dirac, if you have ever heard of it, who was, if you ever gone to England and at the Abbey, you sort of see this small little plaque at the bottom and has this Dirac equation there. So it's one of the most beautiful equations in physics. Basically, I'm not ready to talk much about Dirac equation, but simply I mentioned that basically what Dirac was trying to do. He was a person who was a pure theoretician, okay? He wanted to develop a theory to describe relativistic electrons. The Schrodinger equation described non-relativistic particles. So he needed a theory to describe relativistic particles, and that's all. He didn't care about spin, he didn't care about anything. He said, I want a theory which is where quantum mechanics and relativity are married together. Just the exact agreement. So he developed a theory anyway. So he comes just using the fact that you have, he was able to actually, he wanted this basically Schrodinger equation. Since you're doing relativity, your space and time should be on equal footing. Your space is one, time is first derivative, and so space should be first derivative. All the details are here, and basically he gets an equation. And now he turns out his wave functions have 4 components. It turns out 2 of them were describe spin up and spin down, and other 2 describes antiparticle. So this is sort of one of the most beautiful things happen in physics, the discovery of antiparticles. just came from the fact that the equations of physics should be simple, beautiful, and relativity should be consistent with quantum mechanics. So now let's see what all this means. Basically what we are saying is, what I wrote here at the bottom, spin emerges as intrinsic angular moment, an abstract quantity, and is not associated with actually something spinning. There's nothing spinning. And physicists, the spinning motion is totally erased in the minds of physics community because from Dirac's theory, the spin emerged as something intrinsic, right? Like just a particle has a mass, it has a charge, it's got spin. What is it? Nobody knows. So it remained a mystery, but it exists. It came out of the theory, right? It was, fundamentally. So anyway, so this is, so basically in the end of 1920s, we have people who are very happy, we understand spin, at least we have an equation which predicts the electron must have a spin. It's a point particle, so it's very mysterious. Nobody knows what that means. Nobody knows what it means in terms of visualization, right? It cannot visualize a point particle spinning, but it's there in the theory. If you demand a theory where quantum mechanics and relativity are consistent with each other, spin is a natural consequence of that. That's the point. Okay, so now we're going to get back to, sorry, I'm going backward, excuse me. Have something good with that. The last part of my talk, which is David Hestenes' thing. You heard 2 years ago, some of you may have heard of him. Basically, David Hestenes was, said it was he took off from where Clifford has left. Clifford died very early, age in 30s, and his algebra was not complete, so he really wanted to pick up Clifford algebra. But let me just kind of summarize the basic things of David Hestenes here. So let's go back to Pauli and Dirac. Pauli and Dirac, the spin is encoded in the Pauli matrices, right? Pauli matrices describe quantum spin. If you talk about Pauli's theory, if you talk about Dirac's theory, it's again something like that. It's called gamma matrices, which are also made out of Pauli matrices. So in Pauli, in 20s, Pauli's theory spin was sort of related to these Pauli matrices. In Hestenes' theory, 1960s, he made a completely different postulate. He said Pauli matrices do not intrinsically have anything to do with quantum spin. What he's saying is Pauli matrices actually represent 3 directions in space. If you're talking about Dirac matrices, which are gamma matrices, they represent 3 directions in space-time. So spin is not intrinsically related to these matrices. So this is a completely different viewpoint. Now I should say this is very speculative, like not a whole physics community has embraced on it, certain aspects, but many have. So I think it's still considered one of the. And as I'm going to tell you in a few minutes, the next few minutes, this picture has some hope that is going to tell us what exactly is spinning. Right? When I talk about quantum spin, what is spinning? Nobody knows because point particles, it's got angular momentum, but what is really moving? So Hestenes has some answer, at least is trying to answer some of these questions. Okay, so the first thing Hestenes does, one of the first things, he does a lot of things, I guess, but in terms of, to me, what's most interesting thing about his work is his applications to quantum spin. Okay, so he says he writes down this, the Pauli 2-component wave function in terms of some spinors, which is actually rotor. It's really a quaternion, like I've written down. He showed that this is actually, maybe I should point out here. So Hestenes proves that what we call Pauli spinor, the 2-component wave function, is actually a bivector, which is really a quaternion. Similarly, if you look at a Dirac spinor, which is a 4-component, the 4-component is nothing, as I said, 2 are spins, 2 are antiparticles. So there's still sort of spin-related things. And again, same thing, they are bivectors, they are spinors. And you can see half angles appearing again here. So they, every time, so this is what Hestenes calls spinors. Every time, so that means you change angle by 2 pi, these things are going to change sign. Right, because the angle actually pairing is half of that. Okay, so the spin is defined to be by this formula at the bottom. So basically, Hestenes' point is spin is actually, so basically what is spin? So these are some fixed directions in space-time, and R is this quaternion or the rotor, and this is how you define the spin. This is sort of how you define, any observable in quantum physics. You take wave functions, take its complex conjugate, but what he does is to actually sandwich this bivector. So we basically, I think in substance, to me, it provides a facelift to spin, because if you look at this formula, R is a rotor, right? So he's directly relating spin to a rotor, rotation at least. So it's very explicit in this construction that spin has something to do with rotation. This was never there in Dirac's theory or Pauli's theory. And in fact, it tells you, so this wave, the spinner actually has this instruction. So he says, takes this bivector in space-time, do rotation, and you get the spin. That's what the spin is. Again, Hestenes' picture, which is, I think, very beautiful. Okay, sorry, going back again, my last, sort of the last slide. Okay, so let's, as I said, mathematically, he has a beautiful picture, and there's no controversy about that. So that part is fine, it's all mathematics, but at least it gives you kind of imagining spin as some kind of rotation, right? Because it rotates space-time vectors. But then Hestenes asks a much deeper question. He's asking, okay, the spinner is a rotor, but what is rotating is a space-time vectors. And space-time vectors are not the spin, right? So he's asking a question, what entity, what is actually spinning? And the rest of this is completely speculative. So let me just quickly mention, his speculation is that spin derived, that electron, spin is actually dynamical property of the electron. So even at, you probably heard of something called 0-point energy in quantum physics. If you ever heard of a little bit of quantum physics, means even at absolute zero, there's some energy. And what Hestenes is saying is that energy is coming from spin. So electron is actually going through some helical motion, and that's what's giving rise to some angular momentum, which is the quantum spin, and also the 0-point energy. So I'm just really going to close my talk with a slide of Hestenes' recent talk he gave in Arizona, where he really talks about his theory. The problem is, it's a beautiful theory, but how do you know it's true? If the electron is really spinning like this, having this helical motion, there must be some signature of that in experiments. So he has proposed an experiment that has been done apparently, but hasn't been, positive conclusions yet. So it's, he's still working on it. Actually, he told me he's writing a paper. After that, everything is going to be clear. The paper is going to come out soon, but hasn't come out yet, but it's in his talk. So thank you so much. Yes, I'll stop.
The paper that I had showed by the Israeli physicist Victor Ariel.
Sorry, which physicist?
Victor Ariel from Israel, of Tel Aviv University. And he actually just defines space-time itself as time as the forward direction, forward vector, not just a real number scale.
I see. Yeah, you were talking about this forward vectors in your talk,
Yes.
Something I didn't fully understand. Yeah, I'm not familiar with that work, yeah.
So the idea is that instead of just saying we have a real number part of the quaternion, we actually define it as forward in the direction of the observer.
Yes.
And one thing all observers are doing, they're moving forward in time. Okay? So he has his Lorentz transformation when you begin to accelerate in space-time diagram. you no longer move truly forward in time, you actually move to the side of it, so your clock stays floating. And the way he has relativity with curvature of space-time is time itself, for all observers in that region, starts to go in a different direction. So I'm just thinking when I'm hearing
But
it,
is he talking about spin? He's not focusing on
what I'm
quantity.
thinking about spin, if we interpret it as forward direction of time, perhaps spin is the helical structure, very similar to Euler's formula there. You send it out in a spiral.
Yeah, maybe I should look up that paper, yes.
Yes, he will very much enjoy it.
Yeah.
And I think the guy is absolutely right. So,
Very right. Thank you for pointing out that.
but maybe believing in him is because I'm believing in his ignorance. I don't know.
Yeah.
So I found it absolutely fascinating.
Well, it's the whole idea is that somebody is at least trying to address this question about what exactly is
Why
spinning.
would this happen unless something is spinning?
Yeah, exactly. And I think that's the beauty of Hestenes' work.
Right.
At least he's speculative, The problem in physics is if you have a theory, unless you confirm it, nobody believes you, right?
Well, hopefully with quaternionic least squares, you can go to the laboratory and start finding out.
Yeah, exactly. So,
Last question, I don't want the people to get the term. When you had the quadratic equation earlier, x plus y squared equals x squared plus xy yx, do you need the closed form solution to that? Because I haven't have no need for it. I can
yeah,
solve the
I
roots.
don't know, yeah.
If you need the roots of the quaternionic quadratic like that, I have the closed form.
Oh, I see. Okay, yes.
And it won't crash if you get the square root of -1 in your discriminant, because the only way that can happen is if the two terms that you're subtracting in the discriminant were both on the same great circle, and if you know that great circle, then it compels the square root of -1 to be the purely imaginary unit vectors.
Yeah. See, right now, I see you have there may be some relevance. I'm not seeing the connection to spin, though, but maybe there is
I thought
some.
you needed the roots.
Yeah.
Spin. So I could do that equation that helps you. I'd like to give it to you.
Yeah. Okay.
Are there any other?
Sorry, any other questions? Yes.
Go ahead.
My question, yes. You were talking about the work of Cartan.
Yes,
with-
Eli Cartan,
with
right.
spinners. I'm more familiar with Cartan's work on the exterior algebra, like in the context of like differential geometry and relativity. I'm wondering if there is a mathematical framework that subsumes both of these things. They seem
So to be honest with you, I know very little. Only work of Eli Cartan I know is the one where he constructed spinners. So I have his book and I find it totally I just don't understand. I'm a physicist and that's just too abstract for me. But I was able to understand his spinner construction because it's so simple as construct a vector of zero length by putting two orthogonal vectors in a complex plane. It's such a beauty, and then define this new spinner, and it's just such a simple, beautiful idea. And that's all, unfortunately, that's the only work of Eli Cartan I understand. Actually, I also know Eli Cartan's work in actually topological insulators in condensed matter physics. His he's done, there's something called tenfold ways classification. So actually, I know one more work of Eli Cartan, which is somewhat relevant based on Clifford algebra. But most of his work is just beyond me, so I wouldn't know that.
Alex has a question.
Sometimes if you consider general relativity with torsion, and it appears that torsion is correlated with spin, and it may be answer to your question. It can be easily verified on experiment because movement of particle by parallelogram will be not close, so it will be not returned to the original place. So on the long time, it will be a very big displacement.
Yeah, so maybe you're referring to, there is something called twistor theory, Roger Penrose theory, which he talks about general relativity, right? And he uses spinors to describe space-time. I think maybe...
Torsion.
Yeah.
Connection is not commutative. And in this case, parallelogram will be closed. While by amount of the torsion on the area.
Yeah, okay, I'm not familiar with it, but maybe it's,
Yeah, but maybe you answer to your question. So what is meaning? Because particle move in the space-time and go where they say,
Some kind of torsion.
spiral.
I see. Yeah. Yes. Thank you for the comment. I should
there-
look into all that. Yes.
Are there any other questions?
Yeah, I was just going to ask, any other questions?
Okay,
Okay, and we
let's-
want to thank Indu for...
Thank you so much.
Thank you very much, Indu.